So yeah, we've got a few people coming through now. Just wait for those numbers to settle down before we make a start. We're making a start in a moment. Just wait for the participant numbers to start to settle down. Okay. I think we've started to settle around 60 participants. So we'll just quickly make a start now. So just welcome you all to this webinar tonight. It's brought to you by the Mersey and Western Cheshire local network of the IET, and more specifically the biomedical engineering group of the IET. I'm Joshua Moore. I'm chairing this event today, and Jack Hayes is also involved. He'll be doing the Q&A session at the end. So the biomedical engineering group, let's see if, we're a group that, well, we're aiming to raise awareness and improve knowledge in this, well, what's a very multidisciplinary field. To achieve this, we want to support industrial advancement through networking. We believe that networking between industry and academia is vital for the progression of this field. We also want to connect individuals and give a voice to active individuals within the field and their companies so that they can share their knowledge. And a good example of that is the talk that we've got tonight from Proto Labs, where they're going to be sharing their knowledge. So the biomedical engineering group, it's fairly young in terms of how long we've been established. And out of this, due to this, we're actually looking for volunteers to help, well, join us in the steering committee. As part of the steering committee, you wouldn't really have to commit more than 5 hours of your time per month, but you'd be able to influence the direction in which our group is heading, help us organise activities and other events. Maybe you'd be able to suggest certain speakers or suggest a talk from a speaker you may want to hear from. You also get some extensive networking opportunities for people in industry and others in academia. We also support registrations for chartership. A member from the biomedical engineering group has actually achieved chartership through their activities in the IET. And it's also a very valuable addition to your CV. So if you're interested in volunteering at all, please don't hesitate to contact me at this email here. And yeah, we can sort that out and it would be brilliant to have you. So today's event is a webinar titled Accelerating Medical Device Development Through Digital Manufacturing. And our speaker is Mr. Tassos Pantelis. Tassos is a highly qualified design and mechanical engineer. And he has, well, over 4 years experience working as part of the applications engineering team at Proto Labs. As part of this team, well, this team actually offers a considerable amount of design and manufacturing advice, both internally at Proto Labs and to external companies as well. Tassos himself has extensive knowledge of all the core services offered by Proto Labs, and these include things like injection molding, CNC machining, and 3D printing. And recently, Tassos has taken on the role as the additive manufacturing champion for Proto Labs, this actually makes him the go-to representative for seeking advice and also understanding the capabilities of additive manufacturing within Proto Labs. Tassos has also regularly featured in trade articles and holds a strong portfolio of technical presentations and papers, which makes tonight's talk something to look forward to. Just a few things to clear up beforehand. This webinar will last, well, the presentation part of this webinar will last roughly 40 minutes, and we'll then have a short Q&A session afterwards. If you've got any questions at all, please use the questions box at the bottom of your screen. If you submit the questions here, we'll be able to see them and we'll get around to answering them at the end of the session. Also note that this webinar is being recorded. There's also the fact that this webinar contributes to your continuing professional development. So if you require continuing professional development certificate, please contact either myself or Andrew Caldos at these emails here, and we can provide you with the certificate. And just a final few points to summarize what we're hoping to achieve with the Biomedical Engineering Group. We're hoping to get people to come to our events. We're hoping to involve lots of companies, involve ourselves in industry, and we're hoping to actively encourage people to join a group within the IET. It may not be the Biomedical Engineering Group, but it'd be great if you could join a group. And if you're interested in any of those things, please don't hesitate to contact one of the contacts at the bottom of this slide. So I'm now going to stop sharing my screen and I'll pass over to Tassos, who will begin what should be an interesting talk.
Thank you, Joshua. Hello, everyone from me. Today, on today's webinar, we'll have some interesting things and we will see how digital manufacturing connects to and relates to the medical industry. We'll see the digital manufacturing and from our perspective, from Protolabs' perspective, and how we can assist in order to accelerate the products to market, and of course some other advantages which will be through the supply chain, and of course we will see some case studies, interesting case studies. We will just see after we see some theoretical things, we'll just go into practice to see real examples of successful examples of how Protolabs helped some specific companies, medical companies, and of course we'll see what we offer, what materials are available, which are the future trends, and generally overall how can digital manufacturing help medical industry. So of course, as Josh mentioned, we'll have some Q&A session at the end of the presentation, so please take notes and we'll try to answer as many questions as possible. Of course, those which are not answered, we will look at that afterwards, and then you will receive a follow-up email. So let's start with an introduction of who are we, who are Protolabs. So first of all, if we had to describe Protolabs with one word, it would be speed. The benefit and all the advantage of Protolabs is just speed and how fast we can accelerate your design and your product development, and this can be done through this main through three main quick turn services: 3D printing, CNC machining, and injection molding. There is an impressive short lead time, especially for injection molding. We can have parts from 1 to 15 days. And this, of course, leads to making and bringing products to life way faster, do some design verifications way faster, having some prototypes in order to get the final product to market way faster. So, of course, this has a great benefit on the supply chain. We can have parts on demand. And, of course, we can start with one process, as we will see on the case studies, and then we can also do bridge tooling and just connect all the processes from 3D printing to the final production through injection molding. So let's see this illustration, just a very minimalistic but very precise comparison between rapid prototyping and traditional manufacturing. So in rapid manufacturing, as it can be seen, we can have prototypes within just a few days. We can have some design iterations very fast and in the cheapest possible, in the most cost-effective way. And this includes mainly the two processes of 3D printing and CNC machining. So after all these prototypes are confirmed, after the designs are verified, then we could move to injection molding to have a few thousand parts. And this, of course, would be fast due to the very short lead times. Injection molding started from 1 day for a very simple part, up to 15 days for more complex parts. There is a big variety of materials, and after all the parts are made, the verification and validation time would need just a couple of months to be confirmed. And all in all, due to the short lead times, we can have the products into market in a very short time. And in this case, we can have even half the time than the traditional manufacturers. So of course, this is because of many advantages. Protolabs has in-house software. Everything is done in-house, so this helps maintain a very fast process flow and making sure that everything starts from the very beginning, from the design after we receive the design until the end when we have the part. So after all this, just a very quick introduction of how digital and rapid manufacturing could help accelerate the products into market, and we'll see now how it can relate even closer to the medical industry. So digital technologies and advanced manufacturing are transforming production, driving a new industrial revolution known as, we all know, Industry 4.0. Now, by creating a digital supply chain, one that's more resilient and responsive to risks and opportunities, this is something very essential. So many companies, as we see, have already moved into this direction. A third of more than 2,000 industrial companies have digitized their supply chains, while nearly three-quarters expect to be by 2022, according to a recent PwC survey. So the advantages include improved efficiency, bigger, greater revenue, and of course, lower costs. Such Industry 4.0 benefits are available today through on-demand manufacturing, and particularly, of course, with a supplier that harnesses digital technologies and advanced automated production processes to produce custom components on short notice, and we'll see, of course, some examples very shortly, on time and cost effectively. So while that makes on-demand manufacturing ideal for rapid prototyping, manufacturing on demand with low volume injection molding can also reduce the total cost of ownership, production for tooling and parts. So why digital manufacturing for medical? There are plenty of reasons to describe why this could be a necessity or a need for this industry. So let's see some things in more detail. So with every quote Protolabs completes, you will receive a free design for manufacturability feedback. This is a very great tool. This is an interactive quote where it highlights all the potential risks that could happen to the part and any design adjustments that need to be made. So it will affect how the manufacturing, it will show how the manufacturing process will affect the parts quality in the end. Our flexibility and automation means that you can use Protolabs for low volume production, bridge tooling, or rapid prototyping. Protolabs manufactures parts using LSR molding, the liquid silicone rubber, CNC, injection molding with thermopolymers, and 3D printing, 5 different processes, including plastics and metals. So we are unbiased and we will direct you to the best manufacturing method for your requirements. Of course, although the quote is fully interactive and it presents a lot of nice details, we always give extra attention to the communication with, for example, like me as an application engineer or my team, in order to get a full understanding of what we'll get and a full understanding of how you could improve your part with regards to both performance and quality. The interactive design analysis. So you can make design adjustments that save development time, of course, and cost with using the DFM feedback on the quote. Also for the low volume production, the supply chain could be streamlined once before and after products are launched to market. We are technology agnostic, meaning that the medical parts are paired with the right equipment and processes regarding different project needs. As we mentioned about bridge tooling, we can have bridge tooling for design and market validation before capital investment is made in tools, and this mainly focuses on the large production tools or the steel tools, which will require much more time to be made, to be machined and manufactured. And with rapid prototyping, just to create prototypes in production grade materials, we can use any kind of material, especially for injection molding, whatever can be injection molding, we could use from the plastics point of view for functional and regularity testing. Of course, let's not forget the very strict certifications that this industry has and requires. And production-like parts, the prototype injection molding creates parts which allow form and function and tests with the same material planned for production parts. So we can use a specific grade to make the part before using the tool for the final production. So it will be a very good understanding and verification of how the part will be in the end. So at this point, let's have a look at the case study. Let's have a look at a very interesting case study with Parker and Hannifin, and let's see how they benefit from digital manufacturing, from Protolabs in this case, and what is the actual product they made. So it all started 7 years ago when then Parker Hannifin CEO Don Vaskevich challenged his team with a question. So what's the future of our company? So this question triggered a flurry of activity to chart out new territory and opportunities that would secure the company's growth well into the future. The initiative eventually led the company to investigate how it could adapt its core competencies in motion and control technologies to develop wearable robotic devices in the prosthetics and orthotic space. So as you can see here on the right hand side, the image of the actual product. So as it explored the opportunity further, Parker Hannifin connected with researchers and Vanderbilt University working to adapt robotics technology to help patients with lower limb paralysis increase mobility and regain the ability to walk. This led to the development of a wearable exoskeleton that consists of a brace worn on the hips and legs and is powered by motors, batteries, and a set of different other electronics. So this happened in 2012, where Parker Hannifin and Vanderbilt reached an agreement to license the technology, and soon after, the company began working to commercialize a robotic exoskeleton called Indigo. Dr. Ryan Faris was a co-inventor in the development of the technology as part of his doctoral work at the university, and Parker Hannifin brought him on as the technical lead for the business unit tasked with bringing the product Indigo to market. So let's have a look at the actual challenges this team met. So one particular design challenge that required quick turn parts was related to a component that serves as a light pipe for the device. This part transmits light from a small LED on an embedded circuit board out to the exterior so that the user can see the device's current status. This lead indicator is particularly important because this is how the actual user, the paraplegic, the stroke patient, or whoever is using the system knows what state they are in, what mode they are in, and what's about to happen with the device. The initial light pipe design was manufactured with a molded transparent thermoplastic. So, however, after a few testing cycles, it became apparent that the material was too brittle to hold up to the rigors of daily use, since the system was designed to flex with the user's movement. So Dr. Faris also explained that the light pipe was a part of a larger assembly, and the relative motion of the assembly did not really cooperate well with a rigid plastic light component. So what happened? They needed a cost-efficient molding option that was optimized for this stage of product development, since design was not yet finalized. So this robotic exoskeleton was still in the prototyping phase, and FDA approvals were still pending. So this would require a more costly investment in traditional tooling, so which was not obviously very ideal. So the team turned to Protolabs, especially for the LSR molding, for the liquid silicon rubber molding, to quickly manufacture a few light pipe components so that they could test the new design and have the flexibility, of course, to iterate if necessary. So the key to accelerating the molding process was, as we already mentioned, the interactive quoting system, which through Protolabs, which shares the DFM feedback, a full interactive quote and quite precise and comprehensive. So this with this tool, they used to upload parts for quotes. The quotes were ready in just a few hours, and then they could go through several iterations until it is within their it was their targeted cost. So this enabled a highly iterative design process while reducing development costs, since it could all be digitally achieved through software and it didn't really require manufacturing final parts. So what was the result of that? So with low volume manufacturing at its disposal, Parker Hannifin has been able to reduce development time, bring innovative products to market faster, and effectively respond to customer feedback. So what we can say is that overall, including molding production parts, um, Dr. Faris estimates that Parker Hannifin's human motion and control business unit has manufactured thousands of components with Protolabs, and of course will continue leveraging its digital manufacturing services in future generation of the product, in this case, the Indigo. So let's now have a look on which service should it be used. It's a very good and very common question when it comes to making prototypes, moving to final production, how we will start, which is the most cost-effective manufacturing process to start with, which is the one that will be the next step in order to have more parts, more complex parts, and so on. So this is a really an economic discussion, which one create the most value for you and create the best business case for you. So again, depending on the requirements of the project, of the application, depending on the time frame that we have, depending on the urgency and so on, for every single section we have different solutions with regard to processes. And of course, this is something that we will see. We'll see different options that they can be offered on each process. So let's see the cost curve comparison between the parts. So we'll see here, you can see on this graph, you see just when it makes sense to use 3D printing and when it makes sense to use injection molding. So of course, there is a limit on the number of parts that is needed in order to make 3D printing cost effective comparing to injection molding. But of course, this depends on other parameters like the parts complexity, the parts size, and so on. So the injection molding, what we can say, it's very efficient and repeatable at scale, but the fixed costs could be quite high. And this, of course, relates to the actual mold that is made. On the other hand, 3DP, the complexity is almost free, but its costs are almost unvariable even with higher quantities. So the curve doesn't scale down as much as injection molding, but the curve is changing, and 1 to 100 gives you a lot of good cases for 3D printing already. So as we can see, 3D printing could be competitive in price with injection molding up to 100 parts, but of course, this could stretch to a higher number depending on the actual part. So and of course the 3D printing process, because it could go up to a few hundreds in reality. So 3D printing is mostly used in the first prototyping phase, or for industries, companies, or products with high mix of and low volume. So it is still a good process to consider for low volume production, but of course, when it comes to a higher number of parts, injection molding is still the king. So, and as we have already discussed, here at Protolabs, we are technology agnostic, so we can offer different processes apart from injection molding, CNC machining, and 3D printing. So we can try and help to utilize each of these processes in the best possible way, from the prototyping stage until the product is launched and the product is coming to a high production, and it requires a few thousand of parts. And this is where Protolabs could still could be competitive, and of course with until the number of a few thousand of parts, but of course after that, um, it could be also a good moving forward would be a good way to move to the final production with steel tools, with big production tools. And it would make sense if some parts will need to be produced in millions, then it could be good to move to um, the another production supplier. So it's a big cycle, starting from the prototyping until the end of the life of the product. But during all this journey, we can have solutions for all the most of the demands. Now, a very good question could be about materials, because materials science, materials evolve every year for all industries. So especially for the medical industry, we can have the high temperature plastics, the high engineered materials like PIC and PEI. These materials could be quite costly, but at the same time they could do very good. They could have great performance with regards to mechanical properties, with regards to chemical resistance, chemical properties, and this would be very widely used in medical industry. The LSR, the silicon, this is the higher temperature resistance material. It has great chemical resistance and stability. This is one of the main characteristics. And of course, especially for medical industry, where parts require to be sterilized and need to be flexible as well. From the 3D printing point of view, the 3D printing ABS, so the microfine green and gray, this is a material that was created specifically for Protolabs, where, and we can see later on a bit more details about this material. So we can have many parts could be realized which are very small. We can achieve parts on the XY axis of the size of 0.070 millimeters. So as you can understand, this is very tiny, and it can benefit on many parts. So the industries or the sectors of the medical industry that could benefit from that would be the microfluidics, and this is something that it is widely used, especially on a material like the watershed, which could be fully transparent after some post processing, and it could be used to prototype this kind of parts and transparent components like for example lenses and housings. Also medical alloys, so between machined and 3D printed metals, there are more than 20 metal material options available for medical components, instrumentation, and other applications. Metals like titanium and Inconel have attributes like temperature resistance, while various stainless steel materials bring corrosion resistance and strength. Of course, it's really worth mentioning here that Protolabs holds the ISO 13485 certification for 3D printing DMLS for titanium and cobalt chrome, and meaning that we can support fully with medical implants. So any kind of parts that require these kind of implants, any products of that require to be made under this certification, we can easily accommodate everything and follow the strict certification rules. So let's see the 3D printing for medical industry. Let's see a bit more about the materials. So as we have already discussed, and I'm sure that you already know, 3D printing is an incredible approach for high complexity, low quantity parts. The ever increasing range of materials makes it applicable for more and more application. So it's being used for prototypes, but at the same time for end use parts. It's also being used for jigs, fixture, and component housings. So as we have already mentioned about the microfine green, so we can have in micro resolution, the actual layer thickness is about 0.025 millimeters. So it can produce very, very tiny parts with very, very good accuracy. So generally, this is a characteristic of stereolithography process in general, and this is something that we can offer. And the type of materials could be ABS-like, PC-like, and polypropylene-like. The reason we mention it's like because they are not purely ABS or PC or polypropylene. They just mimic the properties because the parts are made in a very low heat process, which is the stereolithography. So the mechanical properties are quite limited. But the silicon offered on stereolithography is a pure and true silicon, which can have all the benefits of this material, meaning very good chemical and thermal resistance, as well as great surface finish and accuracy. For the 3D printing metal, for DMLS, plenty of materials to choose from for every need: aluminum, cobalt chrome, copper, inconel, steels, two set of steels, and titanium. For the polyjet, the digital photopolymers, again, there are materials which are rubber-like, they can mimic rubber, and in a different different values of short hardness values, starting from 30 to 95. And of course, we can have overmold options as well. We can have parts, two materials made in one print. And of course, rigid materials which mimic the acrylic. And the more cost-effective options, which are the SLS and the MJF, which are powder-based materials, plenty of materials to choose from, especially nylons, 11 and 12, very very good materials in terms of performance, heat stability, flexibility, impact resistance, and of course we introduced recently the DPU for MJF, which is in 88 short hardness. So all these materials, there is a wide variety of materials to choose from, which could accommodate depending on the application requirements and needs. So let's see the design goals which are likely to work for each company. So the benefit of all these are with 3D printing and the generative design is that we can have lightweight parts, we can reduce material, hence cost, but by keeping the same performance, structural performance on the parts. The combination of assemblies, the reduction in labor and the increase in yields. Of course, we can, the more complex parts, the better for 3D printing, because this makes the parts more cost effective, but at the same time eliminates secondary operations. Although there is a big list of secondary operations, we can still make the parts good at the first time. The part performance, of course, is improved, and while we maintain the material properties. And of course, we can the supply chain could be optimized. We can have parts on demand anytime. With there is no need, absolutely no need to stock or to store any parts, which it's unknown when they're gonna be used. Um, and of course, more purposeful design for whatever your needs are. And of course, it's a great opportunity to review and examine and unlock new sources of revenue or customer base. So at this point, let's see another case study, which is not really a case study, but it's a great example of how a part could start, how a design could start as um, a very conventional approach, and how it can be drastically improved during the generative design, and of course, the benefit on 3D printing producing it. So it's all about personalization. So 3D printing allows personalization. As you can see on the images, we have a simple part and how it can become. This, of course, has a great benefit on the material reduction. It increases complexity, but at the same time maintains the performance of the part. And if not, it gets better. There are secondary operations which could benefit medical industry, and these are the vapor smoothing that we offer. So this process makes the parts smooth and more impact resistant and chemical resistant as well. They could be used also for some FDA approved applications. So um, it's a great combination of process 3D printing process and post process like the vapor smoothing. So all the efficiency and the complexity of the design could be easily realized, but at the same time we could have a great surface finish, very close to injection molding parts, as well as great chemical resistant properties. So another real example would be this part we show here. So it's a great example of highlighting how the part cost could be reduced through 3D printing, and of course with designing smarter. So on the left hand side is the conventional design, and on the right hand side how this design was improved, and of course the benefit, if we have to say it in numbers, is that the part volume is reduced, the build time is reduced, the finishing time, the post-processing time is drastically, significantly reduced, and the total cost is way lower. So to use the full capacities of 3D printing, you must be familiar with design for additive manufacturing, or of course rely on some experts like our application engineering team and some CAD specialists. So the design guidelines, we have plenty of resources, and we'll speak about that later on the website, and some tips and tricks on making your design and more efficient. And it doesn't mean that if it gets complex, it would be more difficult to be produced, but it could be even better on the long run. Beside the part itself, there are other places where 3D printing can help you save money and really get economic value. So to further improve overall cost reduction and improve um, part efficiency, we need to not only have a product design perspective, but we also need to embrace a system design one. Then two value streams become visible. So the first one is the entire cost of manufacturing. There really isn't a standard for what materials costs are as a percentage of the total. So we're using 30% as a part material cost as an assumption. In your industry, it may be more or less. The rest could be overhead, shipping, assembly, etc. And as you can see, the parts are a relatively low percentage of the overall cost. So if we can decrease the number of parts on the assembly, the overall cost comes down very quickly. So this is the benefit of 3D printing. We can consolidate parts. Instead of having, for example, 10 pieces for one part, we can have just one, which has the same functionality as um, the original one. Secondly, you can help with um, uh, someone, with customer or the companies with their total costs. So we are using 45% as a rough gauge of that purchase cost within total cost of ownership. Think of that as depreciation and interest of that purchase. So in this case, the part itself is only 10 to 15% of the total overall cost that your customer cares about. So certainly has a very good impact, but not the biggest areas, of course, that you can influence by utilizing the flexibility that 3DP gives you. You can customize each part to reduce the cost of ownership or running costs for the customer. But let's remember that the true and biggest benefit comes when um, we can unlock a new design, a new process, or a new benefit that it couldn't be achieved with traditional manufacturing. So once again, digital manufacturing, rapid prototyping helps getting products faster and, more importantly, very cost effectively. So let's see another case study of another company, which is really interesting, and I believe it will give a great value to you guys that if you haven't seen that. So it's about an implant. So as we know, our body is very tolerant of titanium, but since it is metal, there is a danger to patients exposing themselves to the sun and too much heat being transmitted into the body. In addition, a titanium structure would not be permeable for tissue fluid from the brain. So for what happened for this patient, the procedure requires special secondary process added to the specification. By including a secondary treatment after manufacturing, in this case cleaning, made possible to use a 3D printing part for this case. So the importance of cleaning is really vital, because adherent particles are released from the body by the slightest movement, which can lead to infection or rejection of the implant. So a completely germ-free environment is a key criterion for the successful acceptance of um, any kind of implant into our body. So it is very important, especially for the cranium brain area, to support or at least not hinder the recovery process. So which are the requirements? So the first requirement is as perfect as to fit as perfect as possible. So this is one of the major benefits of additive manufacturing, because the layer by layer, as we know how it works, the layer by layer manufacturing by a laser, in this case 3D printing metal using the MLS, we use a fiber laser with the titanium is hardened on a piece by piece basis, lends itself to maximum customization of shape and size. So this can be fully customized for the specific patient. So as well as the need for a perfect fit, there were more challenges along the way for this company, for Novax DMA, who partnered with Protolabs during the challenge to create the perfect possible part. So due to the size of the patient's hole in the cranial bone, the solution included integrating the biological function of the implant while minimizing heat transfer into the brain tissue. So it was very uh, very precise um, part, which had to be um, no less than perfect. So what was the solution? So after Novax and Protolabs worked together and evaluated all the aspects and requirements of this project, so they came into the conclusion that only a porous structure would exhibit the required properties. So the result involved a grill-shaped implant, which integrated fixing lugs for the cranial bone. This will allow liquids to permeate it and of course enable growth of the bone. In addition, this design has an insulating effect, so the conduction of heat, which is very important as we mentioned, into the interior of the cranium is minimized. So what about the dimensions? The pinholes themselves are approximately 1 millimeter wide. The grill width is about 0.2 millimeters. So after the basic structure was confirmed, the medical technology specialist took over. So this is at the second stage in order to fully make the part perfect and according to the medical needs. So the outcome was to create a perfect cut, a very tailored implant with a porosity of 95%. So the result, the desired result, was the liquids could pass through and the bone tissue could fuse and grow with the implant. So everything was very successful, and of course for the future it worked really well. And the key highlight here is the lead time. So the lead time, this was something that the data preparation and the manufacturing took only 2.5 days, not even 3 days. And the logistics and generally the coordination took 1 week, and the transport 1 week. So in this very crucial surgery, very crucial situation, 3D printing worked at the best possible way. And of course, a company as Proto Labs helped in order to bring this to life with the least possible challenges. So this is again a great perspective, meaning that technology itself is not only cannot only do miracle, but by collaborating and sharing the expertise as a company to the engineers, depending on the project, we can bring products into life and of course save lives as well. So a very important, very nice product. Now, I believe after this introduction, this main case studies and some more information about what can be done and how the digital manufacturing could assist medical industry on many ways, I believe we can all answer why digital manufacturing is a good fit for medical. Also, how can digital manufacturing streamline the supply chain, and of course, which service to use. So, since we are going towards the Q&A session, it's a good opportunity at this point to mention that we have a lot of resources on our website. It's a very good opportunity now that you can download and your free digital manufacturing for the medical industry ebook. It's a very nice piece of information, and I believe it will give a very great value to you. And apart from that, there are plenty of design aids. We have plenty of other case studies on our website. We have some white papers with specific training material for each process, some design tips for each of the processes, some tricks on how you could make the design even better in order to have a more cost-effective solution. But of course, the most important is that you have the information, but also you could have the support by us, as engineers, application engineers in Proto Labs, in order to accelerate even more your project. So I believe now we could be ready for the questions, the Q&A session. So I hope you all had some notes, some questions throughout the presentation. Of course, good to mention here again is that if we don't manage to answer all the questions, we can follow up with an email in a few days' time.
Brilliant. Yeah, thank you very much, Tassos. So yeah, we'll go to the Q&A session now. Any questions that you have, just put them in the Q&A box at the bottom of your screen, and we'll get around to answering them. So I'll hand over to Jack now, who will handle the Q&A.
Thank you. Great talk, Tezos. I'll just, whilst people are putting questions down in the Q&A box, I'll just kick you off with a few general questions, if that's okay.
Of course.
So you were talking about your material called microfine green. I was wondering if you could talk through the applications that someone might be able to use it for, and how that would be relevant to medical devices.
Yes, of course. So the microfine green is a specialized material which was created in collaboration with a material supplier and Protolabs. So this is a stereolithography material. Stereolithography is used for high accuracy and very good surface finish. And this material specifically has a micro resolution, meaning that the layer thickness is 0.025 millimeters. And the smallest feature that we can make is of the size is 0.07 millimeters. So with regards to the actual applications, any medical devices which involve very small features, very small internal channels, for example, any other features or design approaches that are difficult to be realized through the traditional methods like CNC, it's a great fit. So because medical industry requires a lot of accuracy, very high accuracy, and very short lead times, this material could be used on making anything that has to do with microfluidics, for example, where we have there is a need for liquid flow through some channels, and things like this. So any devices which are very complex and which would require some internal design features, microfine green would be a very good fit.
Thank you so much. And I suppose the kind of easy question is always around kind of like certification and medical device regulations. I was just wondering, as a company, what steps have you made towards that so far?
Yes, I can have a look. Could you just repeat that?
Yeah, so in terms of certifications.
Yeah. Yes, certification. Yeah. So about certification, yes. So as we mentioned on the presentation, Protolabs holds the ISO 13485, which is a certification for the production of medical implants and instruments. And this includes some standards. There is a certain process flow, certain requirements that we need to follow in order to make sure that the final products meet these standards. So this is something that we have. This certification applies for titanium parts and cobalt chrome as well. So these materials are widely used in the medical industry, and of course, when we're dealing with implants, we can have the parts ready to be used for all these demanding applications of medical industry.
Fantastic. And then I suppose my next question really is about measurement and inspection, and how would you is there anything you could do to improve the medical part quality?
Of course, that's a very good question. Thank you for highlighting it. I believe it will answer a lot of things here. So we do offer quality inspection reports. So this can be included on the quote. There is no additional charge for that. We offer also detailed measurement reports and part approval process package like the PPAP. This is widely widely required, and which is a standardized process which documents the production, the process, and reproducibility. So with regards to the equipment, we do have a CMM machine. We have 3D scanners where we can have very good and detailed measurement of the parts. This, of course, refers to the injection molding service, but measurement, the quality could be done in 3D printing as well.
Mm-hmm. And have you got any comments on how vapor smoothing could improve medical part quality?
Yes, it's something that I mentioned through the project, through the case study. Of course, it's just it's a good question just to make it a bit more describe it in a more detail. So the unfinished components produced by 3D printing, they have a rougher surface, and this, of course, I refer only on the powder-based materials, which are the process of SLS and MJF. So although we have very good accuracy as well, we have very good material performance, the actual surface finish could let down the application or the project. But with vapor smoothing, this is a fully chemical process, a very easy process, which has a benefit of creating as smooth as possible surface finish on the outer faces of the part, and it matches. It is very close to injection molding parts, but of course, by no means it's exactly the same. But it's a great improvement. And to be more precise about the medical industry, when the parts could easily come or often come in contact with fluids, or cleaning would be required. So with vapor smoothing, we can sterilize the part, we can clean the parts, so without keeping any chemical. So the actual product that is vapor smooth, the actual 3D printing component, doesn't it's not that porous at all, because it is fully airtight and watertight, meaning that the part could easily be used for really hard applications.
Perfect. Thank you so much. So looks like we've got a few questions in the chat now, which is great. So I've got one here from Alex Wood, and he says, on one side, you mentioned using aluminium tooling versus steel tooling for traditional manufacturing. And he wants to know what, to your knowledge, are the relative pros and cons of aluminium and steel tooling?
Great. Yeah, that's a very good question, and purely injection molding, but it's something that sometimes is missed. So we here at Protolabs, we do aluminium tooling. So generally, aluminium tooling, because it's a softer material, it can be machined easier and faster compared to the steel tooling. On the other hand, the steel tooling, because of the actual material properties, it can withstand, it can create more complex tools overall. It can create many more parts, so its life could be many more thousands of parts compared to the aluminium tools. But of course, the other very important aspect is how the heat is distributed, and is the thermal conductivity of the materials are both very good. But the aluminium tool, the benefit is that it can be machined very fast, and of course it is soft enough to be machined, but strong enough in order to have thousands of parts. If we have to make a direct comparison, I would say that the steel tooling is usually used for the production runs, for when we're talking about hundreds of thousands of parts, because it is more reliable over time. It can could withstand, higher forces, higher pressure, and it could be very good for reliability over time. But the drawback of the steel tool is that it requires more time to be built. And of course, when we're dealing with multi-cavity tools, when we deal with more complex parts, more complex components, this will take a very big amount of time, and affect the production timeline. But of course, this is where Protolabs could be as a bridge tooling. This is what we call bridge tooling. So we can have a few thousand parts made, while the production tool made out of steel is machined and is created.
Thank you so much. Really great answers. Just looking at the time, I think we're just about running out. So would it be okay, Tezos, if you had a look in the chat and just kind of answered any questions that are just
Yeah, of course.
unanswered at the moment? And then
Yeah,
I'll hand back to Josh to close out the session.
Perfect. I believe, yes, I see quite a few questions, which is very good.
Yeah, should we agree to answer maybe one or two more, and then we'll close the session?
Yeah, let's have one more. Let's have one more.
Brilliant.
Sure.
Okay, so let's see. Let's see. There are so many and so nice questions. It's really tempting to choose more than one. Let's see. So yeah, I see. Let's have a CNC question which we didn't have. So I see from Mark. So what CNC machine capability do Protolabs have, and how is the CNC programmed come from model perhaps? Okay, so as I mentioned during the presentation, we have created an in-house software. So all the mold design, the tool pathing is done through our software, so we don't use any external sources or any external software. So this means that we have full control of the process, and we can achieve very short design times. Now, with regards to this, the capabilities is we have both metals and plastics. For plastics, we have 3-axis milling. And for metals, we have bigger flexibility and more variety, meaning that we have 3-axis machining, we have 5-axis machining, and lathe option as well. But this only for metals. Unfortunately, for plastics, we have only the 3-axis option. But again, we do have the 3D printing as an alternative in case we have more complex parts. So yeah, I believe I see very nice questions, but due to the time constraint, I would say I'll make sure that all of these are answered and will be distributed, guys, to you in the next few days.
Brilliant. So I think all that's left to do now is say thank you very much for attending, to everyone who has, and thanks again to Tassos for a brilliant talk. Very interesting. And we'll just end the session now. Thank you to everyone. Goodbye.
Thank you, everyone. Bye-bye.